Okay. So, добрый день again. So, short introduction about me. So, I do mostly what we call DevOps, which means nothing and everything simultaneously. One of my big endeavors is to run everything into containers. So while Docker was initially about running back-end applications, we're making some experiments to run desktop applications, to run GPU computations, to run network appliances, all those things within containers. We even have some experiments to run Docker on a virtual machine, have that virtual machine running in Docker, and that Docker would be on a physical machine. And if you want, you can run Docker on top of the other Docker. So you can do Docker, in VM, in Docker, in physical machine. And then you don't exactly know where you are, but it's funny. So this is what I want to talk about today. First, why containers? Because that's one of the key things is to understand why we want to put things in containers. Then I will compare the communication mechanisms that we have in containers and in virtual machines. And then that will lead me to talk about some of the high-speed mechanisms that exist in containers. And those mechanisms will give us new ways to do service discovery and load balancing. All right, so first, why should we use containers? Why is this interesting at all? So containers, there are a few reasons for using them. First, they are great as a packaging format. So you can take your application and all its dependencies, put that in a container, and run that container anywhere. Just like you could do with distribution packages, except that we found out that it was easier to build a container than to build a Debian or RPM package. There is a little downside, is that if you run 10 containers on your machine, as opposed to 10 services on your distribution, you end up with 10 copies of a Linux distro, so you use more disk space. But disk space is cheap, so that's not a big problem. Another nice thing with containers is that as we moved from old-style LXC containers to something like Docker, one of the things that Docker added is some extra metadata. Instead of just being, this is a container, this is just like the root file system, and now you can do anything you want with it, the metadata tells us this is the command that you should start when you start this container. This container wants to run Nginx, and so to start it, you should run Nginx dash some options. Or this container wants to run Apache, so it should run Apache dash other options. It also defines which network ports are listening in the container, so that then you can plug that container in with a load balancer or service discovery or other network mechanisms. So when you have your application in a container, when you want to install it, it becomes a Docker pull. I took Docker as an example, but that could work with another system. So you don't worry anymore about we need to install this and this and this before we can run the service. You just pull the container image. When you want to start it, instead of wondering, should I do /etc/init.d/nginx start, or should I do service nginx start, or should I do systemctl something? No, you do Docker run, and it takes care of everything. Same thing when you want to stop the service. You do Docker stop or Docker kill, and it will take care of the extra processes. No more issues with, I stopped the service, but there is still some processes remaining behind me. Same thing if I wonder, is my service really running? I can know if the main process is still here, and when you are in a container, when that process goes away, everything else is killed. So there is no half state. It's 0, it's stopped, or 1, it's running. There is nothing in the middle. There is no zombie process remaining behind, or the master is there but not the workers. And if you cause a problem with your service and you mess up the configuration or you remove some files and you're like, how do I go back to a clean state? With a container, there is no problem. You just restart the service you Docker run, it creates a new container from the image, and that's it. Another good reason for using containers is that there is no overhead. Well, there is almost no overhead. Or rather, to be more accurate, there is some overhead, but you can get rid of it if it's a problem for you. If you, for instance, in containers, you have some overhead for the memory accounting, but you can disable it if that's a problem for you. There is some overhead for I/O, network and disk, but same thing. You can get rid of it if it's the bottleneck for your application. Another good reason to use containers is that they make it easy to implement immutable infrastructure. The idea of immutable infrastructure is that each time I want to change a tiny little line of code, like I want to change a typo in my website or something like that, I will make a new image, I will create new servers, I will switch my traffic to the new servers, and then I will destroy the old servers. It seems like it's a lot of work compared to just logging into the server and changing the typo. But actually, that's great, because it means that if you do some manual upgrades on your machine, well, you don't do manual upgrades anymore. You make new image, deploy the new image, and switch traffic. So you don't end up with, oh, there was a problem during the upgrade, and half of the servers are running the new code, and the other half is running the old code. It's more an all-or-nothing situation. Or even worse, you could end up with, OK, so we applied the chef cookbooks on our servers. We have 200 servers that are fine, 50 servers where the installation of the new SSL package failed, 30 servers where the git clone of the repo kind of failed at some point, so now they are just broken, and also those 10 servers, we don't know what happened. With immutable infrastructure, you create new images and you deploy them. The problem is that immutable infrastructure sounds like overkill, like creating 100 new VMs each time you change 10 lines of code. It really sounds very expensive. But with containers, it becomes cheap and fast. So containers allow you to implement a good idea, which otherwise would be too slow or too expensive. It also helps you to implement microservice architectures. So is it another hipster buzzword? Microservice architectures, the idea is to break down a big application into many small independent services. This is interesting because if you want to change a small part in your application, instead of redeploying everything, you just redeploy that service and you don't change everything else. This is great because if you're doing like a continuous deployment, like always deploy master from your Git repo, you need to make sure that everything is always working. Maybe you want to deploy the new search system, and then the team working on the user management tells you, no, don't deploy now because our code is broken. So you don't do that. So if you have microservices, each of those components will be isolated, and you can deploy your search thing as much as you want, and they can deploy their user system as much as they want independently. Supposedly, it also lets you, instead of having one big team, have many smaller teams. And Jeff Bezos, the guy who made that small American company, Amazon, he told that there was something called the 2-pizza rule. It means that if a team is so big that it needs more than 2 pizzas to feed them, then the team is too big. There will be too many people, communication will be too hard, you will waste too much time in meetings and synchronization, so the teams should be small. It means that the services should be small, and you should have many small services with small teams, rather than one big thing with one big team. Containers help there, because when you have many small services, deployment becomes a problem, because when you want to deploy the whole application, you have to deploy 10 services. So you need a fast and efficient deployment system. And that's exactly one of the advantages of containers. So when you have containers, once again, it helps you to implement something useful. Okay, so now let's talk a little bit about the technical differences between containers and virtual machines to see what's so special about containers and where it will lead us. So virtual machines, in the beginning, they would emulate CPU instructions, which would be extremely slow. They would emulate the hardware, which would also be extremely slow. And they would use as a normal process on top of a kernel, which means this time you need to communicate with the external world. You need to make syscalls and transition between user and kernel, which is also extremely slow. So they improved a lot. Now, when you run a VM, you run on the same kind of CPU, so there is no CPU emulation. We have para-virtualized drivers, so we don't emulate old-style chipsets to control the disk and the network. And instead of running on top of the kernel, generally they run on top of the hypervisor, so it's much more efficient. There is still some overhead, but it's much better. If we compare that to containers, containers are just normal processes isolated from each other. There is no extra layer between the processes in the containers and the kernel. In many scenarios, when you have a container trying to do something, instead of going through extra layers of isolation, there is just a check in the kernel to see, does that container have access to that resource? A little bit like a UID check. So this is extremely fast. If we make a comparison, in both cases, the code runs on the native CPU, so no overhead, but on a virtual machine, you have para-virtualized devices, while in a container, you just do a normal syscall to open, read, and write your data. In a virtual machine, you hit an hypervisor, while in a container, you directly talk to the kernel. And again, the hypervisor doesn't have a lot of overhead, but some benchmarks will show you that you will have some latency issues. Sometimes the hypervisor will stop the VMs because it needs to do something on its own, and so you will have a little bit more of latency. So on virtual machines, when you want the virtual machines to talk to each other, it's a little bit complicated in some way because there is a very strong isolation. A virtual machine cannot just go to another virtual machine and access its data. So generally, you want to use a network protocol between the two virtual machines. You will use some TCP sockets going over virtual network interfaces. We know that there are some special ways like PCI pass-through so that you can access physical devices from a virtual machine. There are also some mechanisms like XenBus so that you can have very fast communication between the VM and the hypervisor or between two VMs. But those are very specific cases. It's not really easy to start to use that. Like if you want some fast communication between your load balancer and your web server running on the same machine, you're not going to implement something with XenBus. However, that isolation means that virtual machines are extremely secure, obviously. In containers, the key difference is that all the different isolation mechanisms can be enabled or disabled. Each container can have its own network namespace, its own network interface, routing tables and everything, or it can use the one of the host or the one of another container. The file system can be private to the container, but the container can also share a directory with another container. It means that we will be able to use normal communication mechanisms like Unix sockets or shared memory segments, which are extremely fast and that we already know how to use. It's not something completely new and specific to VMs. So what kind of communication mechanisms do we have between containers exactly? So the first one is shared localhost. It means that when you start a container, you can reuse the network stack of another container. So you can start, let's say, a Postgres container listening on localhost, and then you can start a Python container with a web application. It will connect to localhost, and it will, by connecting to localhost, it will reach the database. This means that those two containers will have a very fast communication between them for TCP or UDP sockets, because when you communicate over localhost, it's even faster than communicating over a fake virtual network interface. It's considerably faster, and it has much less CPU overhead. If you do the benchmark on your machine, you will see, OK, communication between two containers, 50 gigabit per second. Communication between two containers with shared local host, 55 gigabit per second. It's only 10%, not a big difference. Now, if you look at the CPU usage, in one case it might be 10%, in the other it might be 2 or 3%. Moreover, if you do service discovery, well, localhost is a well-known address. It means that if I take my example of Postgres and Python web application, when the Python web application wants to connect to the database, it just connects to localhost. Instead of wondering what's the address of the database, I don't think, I just connect to localhost because that's where it is. Another mechanism is a shared file system. You can start a container and you can say, OK, I want /var/lib/Postgres to be shared with another container. And that directory can contain all the stuff that a Unix directory can have. So not only files, but also FIFOs, Unix sockets. So when you want to connect to something, you can connect over a Unix socket, which will effectively create a kind of hole or a communication mechanism between the two containers. And it will be just as fast as a native Unix socket on the same machine communicating between two normal processes. If you want to have extremely fast communication between two containers, you can even use shared memory segments. So you just create a file on this directory, which is shared between the two containers, and then you map the file in memory in both containers, and you have some memory shared between the containers. And there is absolutely zero overhead when you do that. The speed will be exactly the same as two processes running directly on the machine, because technically, it's two processes running directly on the machine. You can also have shared IPC. So I don't think that a lot of people are still using IPC, so we'll just go straight to the next one. You can also, because, well, shared localhost is great for two containers that want to talk to each other, but if a on the same machine, I mean. But if a container wants to talk to the outside world with a good performance, how do we do that? Well, the container can use the network stack of the host. In that case, it will be able to use the network interface, the IP address of the host itself, without any overhead, without any performance penalty. So if you want to run a CDN pushing 40 gig per second from a container, with that you can do it pretty easily. You can also use file systems from the host, because just like the sharing that can happen between two containers, it can also happen between the container and the host. So if a container needs to have extremely fast access to some storage device, you can mount that device on the host and then bind it inside of the container. You can also share access to device nodes, so to virtual or physical devices from the host inside the container. A few examples are raw block devices, if you want to run a Ceph storage node inside a container without overhead, or the video special devices to run GPU applications within containers, and DevKVM for the example I was mentioning in the beginning to run VMs inside of containers. So what does that lead us to? I mean, OK, we have plenty of fast sharing mechanisms, but how does that help us with service discovery and load balancing? So that's exactly what I want to talk about. The fact is that service discovery is not a new problem. If you deploy any kind of really big application, you will have many front ends and back ends and many instances running everywhere, and you will need some kind of service discovery. The thing is that when you start to use containers, the number of services, the number of things will be very big, even for small applications. A traditional small application is like one web server, one database server. In that case, you don't really need service discovery. With containers, very quickly you will have the database, you will have the front end, but you will probably have multiple front ends because you will want to use immutable infrastructure, so each new version equals one new server. You might end up adding some caching and some other services, and each new service, instead of just installing that inside an existing server, will be in a different container. So even simple applications could quickly have 10, 20, 30 containers, and then you will need some kind of service discovery. So the point with containers is that the isolation that they provide let us use some things that were not possible before. For instance, you can inject name resolution entries inside the containers. For instance, you start the web container and you want it to be able to connect to the database. So you will take the address of the database and you will put that in /etc/host. And you will set DB to be an alias to the IP address of the database. So now inside of your code, instead of looking up the address and connecting to the IP address of the database, you just connect to DB, and that works. On a normal system, you don't really want to do that because it sounds like a kind of a hack. In a container, it's not a big problem because when you set those aliases, you set them only in the context of one container. It means that on a single machine, you could start like 10 copies of some application, each using a different database, each using DB as an alias to the database, but each container will have a different /etc/hosts. And so this mechanism, which was really not a dirty hack, suddenly becomes something which works, which doesn't pollute your host system, and which is really, really convenient to use. There are some issues with that, however, because with DNS or with /etc/hosts, you can't push some changes to your application. If the database is moved from a machine to another, or if you do a failover, then you have no way to tell your application, hey, wait, you have to resolve again DB and to connect to the new address. So the solution is generally to just restart the container. A variant is to use environment variables or DNS survey records. It doesn't really improve the situation. It just helps with the port number, because when you have just a DNS host name, it doesn't tell you on which port to connect. So you typically connect to the default port. So 5432 for Postgres, 3306 for MySQL, and so on and so on. So with survey records or environment variables, you can also specify a port. But so before looking at the mechanisms that are more interesting with containers, let's look at what people typically do when they have a large-scale application and they want to do service discovery. They will use a configuration database, something which will be highly available, will have OK performance, not crazy fast, but OK, and something like Zookeeper or etcd, for instance. It's a key value store. You can put the address of your database inside of this configuration system, and then the other applications will get this address and connect to it. And those systems, at least both Zookeeper and etcd, implement some kind of watch so that you can watch this given key with the database address, and if it changes, you can be aware of the change instead of having to poll every 10 seconds, for instance. That's nice, except that you have to change your code significantly if you want to do that. Instead of just doing connect to the database, you have to do connect to Zookeeper, get the address of the database, connect to the database, and then start another thread, process, or coroutine, or whatever, to continue to watch this. And if it changes, then you need to signal your process to reconnect to the database. So that's a lot of changes. And it means that if you, so typically you will write a small library to do that for you. But if you want to support multiple languages, it means writing multiple libraries. And if you want to change from Zookeeper to etcd or the other way around, or, well, then it means rewriting all those libraries. So not so great. So the solution with containers is to use something called ambassadors. So ambassadors sounds, again, like a fancy name. So before explaining what ambassadors are, let's look at the initial scenario is that I have a machine, and I have two containers on that machine, a web container connecting to a database container. And they use like the shared localhost mechanism that I was describing, so it's extremely fast. Actually, it's just as fast as having both programs installed directly on the host. I want to go to that kind of scenario where I have two different machines. I have one machine running the database, one machine running the web front end, and I want the web front end to be able to discover the database and connect to it. So ambassadors are those two containers here. If you don't like the word ambassador, you can say proxy or relay or wiring. The idea is that the web container will connect to the local ambassador or proxy, relay, whatever you want. That one will make a query to something to say, hey, where is the database? That one will receive the query in some way and say, well, I have the database, so I can connect you to the database if you want. So the connection will go to that one. That one will discover the exact address of this other ambassador, and that one will connect to the actual database. The first problem that we have is, what do we want to use here? How do we want those containers to discover each other? How should that really work? So initially, we thought about using cats riding unicorns and throwing fire. But for real, people started to implement specific solutions to that with very different mechanisms. There are two big families of ambassador systems. Some of them are using highly available key-value store like Zookeeper and etcd. And in that case, the idea is that this container will register itself in Zookeeper, for instance. No, sorry, that one. The one with the database will register itself in Zookeeper. It will say, the database is at this host and this port. Then this one, when it needs to connect to the database, will look into Zookeeper, and it will find the address of the database. Another solution is to use multicast. In that case, that container will send a multicast request to say, hey, who has the database? That one will receive that request and will reply to say the database is at this address. Depending on whether you can or cannot do multicast, can or cannot afford to have an extra service, one might be better than the other. So one thing we hear a lot, like on downside of the ambassador system, is, well, you are adding extra layers here. So the latency, the throughput will be slower, and we need to have high performance, and we can't afford to have that, so that doesn't work for us. The thing is that the communication here between the ambassador and the app, and here between the ambassador and the database, will be using one of those fast communication mechanisms that I was talking about. And so the overhead will actually be extremely small. If you compare the cost of communicating between two machines and the cost of communicating between two local containers using a shared network namespace, that one is less than 10%. It's a few percent. The exact numbers depend on whether the communication here is over like a local 10 gig link, or if it's a 1 gig link spanning multiple switches and routers. So, but the idea is that, okay, yeah, sure, we added two new containers, and instead of communicating directly between the web server and the database, Now we are doing blank, 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 blank. But it's OK, because that link and that link are so fast that when you look on the time graph, they are almost invisible. And however, they allow you to decouple the complexity a lot. That's the point where I want to go. Well, it's supposed to be OK. That's the point where I want to go, is that we can separate the logic of discovering the other services and load balancing them from the application itself. Before, we would have to run something special in addition to our application to register it, to discover the database, to register the new version inside the load balancer. And so our application would be different between the development and production scenarios. What we want to push forward is that you will be able to use the same container in dev, QA, staging, production, and all the details, which are big details, but like how you discover other services, how you load balance the traffic, can be in other containers sitting right next to those containers. That's why those fast communication mechanisms are actually important and useful, because if we didn't have them, we couldn't do that. People would forever dismiss those methods, saying that they add too much overhead and are therefore useless. So the key thing is that so containers help us to do deployment. They help us to separate all those service discovery load balancing tasks from the key application code. And that leads us to help us to implement microservices and immutable infrastructure if we want to. And that, in turn, lets us deploy faster. This morning, when we had the panel about Docker, one of the big reasons for some people to use Docker and containers was not necessarily about consolidation, lower cost, or whatever. It's to reduce the time it takes between the moment you commit your code and the moment it hits the production servers. We want that to be as short as possible, and containers themselves don't directly do that, but they let you implement new patterns, which lets you do that. So that's it. I hope you have some questions about that.
Thank you, Jerome. Merci. Вы можете спрашивать вопросы на английском или на русском. Если вы будете спрашивать на русском, я постараюсь перевести ваш вопрос.
Hello, thank you. The main question is about you talk about a lot of pluses, cons, but what about pros? Sorry. What's the problems? What's the issues? What's the main issues with Docker containers? Because you talk only about the good reasons to use Docker, but what's wrong with Docker? What's issues? What's problems you have? Okay, it's one question, and another question about the systems with stateful systems. How to update big stateful systems like database.
So the first question is, OK, so that's a lot of upsides, but what are the downsides of containers? So some of the downsides, I think for me, from my point of view, the main downside is that it's fairly new. I mean, containers themselves are not new. They probably, on Linux at least, there have been containers for like 15 years. But the new thing is the way we are using them now, especially, and it's pretty hard to convey that, but the fact that we can share some things between containers to have high-speed communication, that's the very new thing that allows you to have new use cases for containers. And the downside is that it's new, so we don't know exactly how to deal with that. Again, this morning, there was a question about, OK, so what about the security? How do we do security now? The answer is we do it differently. And the kind of bad news is that since containers, or at least this way to use containers is new, then we don't have yet all the tools that we have for normal systems. So there are a lot of things where we will have to invent new tools. We know how, we know what needs to be done, but it's not always done already. So in my humble opinion, most of the downsides will not be about technical things like, yeah, there is security, there is... the real thing is that it's new and we haven't thought about all the tools that we need. But even security, it's often quoted as one of the big problems of containers. And it's not a big deal because you can work around the issue. You can lock down containers. You can say, I will put my containers in VMs. There are ways to solve that, and it will improve. The real problem is that containers, we are starting to use containers in very new ways, and we still have a lot to learn. The second question was about how to deal with stateful containers. So when running like a database inside a container, the answer is that when people start to use Docker, generally they start with small stateless applications like a small web server, and they say, wow, this is great. I can start a container really fast. I can build it. It's great. It will solve all my problems, and soon I will be able to retire on a small island with a beach and everything. And then they realize that, no, it doesn't solve all the problems, and suddenly the problems linked with stateful containers, would typically the fact that when a stateful service goes down, then, well, it goes down. Those problems appear as bigger than they were before. Because we already had the problem before containers. How do we deal with a stateful Postgres or MySQL database? Well, we set up a replication. We set up failover one way or another. It can be manual or automatic, but we do something. And the answer is, well, we just do exactly the same thing for containers. And we can have the feeling that containers will make something magical for us, because in the beginning, the first experience is great. But no, containers just make some things easier. But some hard problems, like database replication, containers help a bit, but they don't solve it entirely. So when deploying and managing stateful services inside of containers, we still have to think about that. We still have to think about how do I do health checks, failover, how do I redirect the traffic to the new failover database. But some good news are that using those mechanisms that I described, we can make that a little bit simpler. Instead of saying, OK, when I do a failover to my secondary Postgres database, I have to reconfigure all my stuff and everything, I can say, no, each of my front ends connects to a local HA proxy. And when I do the failover, I just kick that HA proxy to switch to the other database. I don't touch my application. I touch this HA proxy, which runs in a different container. So I separate cleanly the different problems.
OK, thank you.
Hello. I want to ask about a slide where you shown 2 ambassadors. I want to ask why do you need the second ambassador which running on the host with the database?
Right. So why do we need to have one ambassador with the web application and one with the database? So the thing is that the communication doesn't really have to go through the ambassadors. There are some scenarios where the ambassador can just be it's here to register the database inside Zookeeper, for instance, but the ambassador itself will be out of the communication path. In that case, you can have the communication go from your web app to the local ambassador directly to the database. So like conceptually, it's going to the other ambassador, but technically it will go directly to the right place. You could even imagine a system where the ambassador on the web server is not involved in the communication. The ambassador is here just to generate a configuration file and restart the application when needed. And then it's not routing traffic, it's just here, it's checking the address of the database, putting that in the config file, restarting the web app, and then it watches to see if the database has moved. And if the database moves, it regenerates the configuration and restarts the web server. Conceptually, it's the same mechanism, even if the ambassador is not involved in the data path.
К сожалению, у нас закончилось время на вопросы. Спасибо большое, Jerome. Thank you very much. It was a very interesting talk. Thank you.